Previously, we looked at NMR at its surface level, but if we actually want to understand how NMR works, we can't just jump straight to things like chemical shift and splitting. We need to understand the very first word in nuclear magnetic resonance. So, chemists, today we can relax and talk about the parts of the atom that aren't just electrons. But honestly, chemistry has spent an incredible amount of time glorifying electrons. General chemistry starts off teaching about electron configurations and bonding. Organic chemistry tells you about electrons interacting in carbon environments. Inorganic chemistry extends that to metal complexes. And by the time you get to physical chemistry, you start questioning what an electron even is. But NMR exists because of the nucleus. So in this video, we're going to build up the atomic nucleus from the ground and understand why certain nuclei interact with a magnetic field in the first place. Because these interactions are what make NMR arguably the most powerful structural technique in chemistry. So we'll start with the atomic structure. In the nucleus of an atom, we have two types of nucleons, protons and neutrons. Right now, I'm showing you the protons in red and the neutrons in blue. The nucleus on the left is carbon-12, and the one on the right is carbon-13. One of these isotopes is NMR active and the other isn't. And the reason why comes down to spin. Now, similar to electrons, nucleons can also be described using a set of quantum numbers. In particle physics, these include things like spin, electric charge, baryon number, isospin, and a bunch of other ones. Definitely more than the 4 that we use for electrons. Luckily for us, NMR is governed primarily by electromagnetism. So the only properties we really care about right now are spin and electric charge. The rest we can safely ignore for this series. But before we continue, we should probably address an important question that's been lingering, and that is, what actually is spin? And honestly, I like the way that Levitt approaches it in his book on spin dynamics. He basically treats this more as an advice than an answer. Because spin is just an incredibly abstract quantum property, and trying to force a classical picture on it usually creates more confusion than understanding. So instead of obsessing over what spin looks like, it's more productive to focus on what it actually does physically and how it behaves mathematically. And the first important thing spin can tell us is whether a nucleus is NMR active or inactive. This equation here gives us the nuclear magnetic moment. A nucleus needs a magnetic moment to interact with a magnetic field. So if that's 0, then the nucleus will be NMR inactive. Now gamma here is the gyromagnetic ratio, and it's non-zero for nuclei that we care about. H bar is just Planck's reduced constant, and that's also non-zero. Meaning the only way for the magnetic moment itself to become 0 is if the nuclear spin quantum number I is also 0. Now, determining the exact nuclear spin for every isotope is actually a pretty deep problem, and the best model we currently have is called the nuclear shell model. And going far down that rabbit hole quickly pulls you into nuclear physics, quantum chromodynamics, and elementary particle theory, which is definitely outside the scope of this video. Luckily, we can still predict NMR activity using a very few set of rules. The first of these 3 is even nuclei. This means the nucleus has an even number of protons and an even number of neutrons. In this situation, the nucleons tend to pair up in such a way that their spin contributions cancel each other out. So the protons cancel, and the neutrons cancel too. That gives a total nuclear spin of 0, making the nucleus NMR inactive. And now we can explain why carbon-12 is inactive and why carbon-13 is active. Carbon-12 has 6 protons and 6 neutrons, even. But carbon-13 has 6 protons and 7 neutrons. And that leads us to the next case, even-odd and odd-even nuclei. Here, one of the nucleons comes in an even amount, while the other comes in an odd amount. So one group fully pairs off and cancels, while the other leaves behind one unpaired nucleon, which contributes to the total spin. These nuclei are NMR active and have half-integer spin values. For carbon-13, the proton pairs cancel, and 3 neutron pairs cancel, leaving behind one unpaired neutron that contributes to the total spin. Finally, we have odd-odd nuclei, where both the proton number and neutron number are odd. Now, neither side fully cancels, so both unpaired nucleons contribute to the total spin. These nuclei are also NMR active, but they typically possess an integer value of spin. Another important thing we should clear up is how isotopes actually present themselves in NMR. Now, when we run something like a carbon-13 NMR experiment, that doesn't mean that every carbon atom magically turns into carbon-13 in our molecule. In fact, most carbon atoms in nature are still carbon-12. Carbon-13 only makes up a very small 1.1% of naturally occurring carbon. So if you had a flask containing an enormous amount of molecules, which you always do, only a small fraction of those molecules would happen to contain a carbon-13 atom at a given carbon position. But because the number of molecules in a tiny sample is astronomically large, that 1% still corresponds to a huge number of observable nuclei. So the signal we detect in carbon-13 NMR comes from this massive ensemble of rare isotopes spread across countless molecules. And this idea becomes really important later when we discuss things like sensitivity and why some nuclei are harder to observe than others. Now there's one major concept we need to move on deeper in NMR, and that's what happens when these nuclear spins are placed inside a magnetic field. Earlier, we said that nuclei can align either with the field or against it, but now we can describe that a little bit more carefully. A nucleus with spin doesn't have one possible orientation in a magnetic field, it has multiple allowed energy states. And the number of those states depend on what we talked about before, the nuclear spin quantum number. So for nuclei with spin 1/2, like protons in carbon-13, there are only 2 allowed energy states. This is where we get that intuition of spin up and spin down. One slightly lower in energy and one slightly higher. This separation of states in a magnetic field is what we call nuclear Zeeman splitting. Now if we move to nuclei with higher numbers of spin, such as aluminum-27 that has spin of 5/2, the number of allowed energy levels increases dramatically. And that's exactly what you're seeing here. As the magnetic field increases, the spin states separate further and further in energy. Now right now I don't want to go too deeply into why this splitting happens classically, because the next video will talk about that. But for now the important idea is this. Without a magnetic field, the spin states are energetically the same, degenerate. Once we apply a magnetic field, that degeneracy is broken and distinct spin energy levels appear. And ultimately, transitions between these energy levels are the foundations of NMR itself.